Our article was on the metal-dependent assembly of a protein nano-cage. Protein-based nanoparticles gain increasing attention as promising materials in nanotechnology, nanomedicine, and materials science. The assembly of protein building blocks, or PBB, into large-scale cage-like structures has been accomplished through different approaches like the design of new protein-protein interfaces, the fusion of oligomeric protein domains, by using de novo designed oligomeric protein domains, and by using de novo designed oligomeric coiled coils to connect together longer natural proteins. These researchers use parallel coiled coils that form well-specified trimeric, tetrameric, and pentameric helical bundles. They assembled a natural trimeric protein into respectively tetrahedral, octahedral, and icosahedral cage-like structures. These cages were constructed by genetically fusing the coiled coil domain to the C-terminus of the natural protein through an oligoglycine linker sequence, and efficient assembly of a protein cage was achieved by optimizing the oligoglycine linker length. A challenge in the design of self-assembling proteins was to control the assembly process. Natural multimeric proteins, such as actin, the vertebrate nuclear pore complex, and viral capsids, undergo environmentally responsive assembly and disassembly. Assembly has previously been controlled by the use of protein-protein disulfide linkages and the design of split metal ion binding sites that span two protein subunits. However, these researchers extended the coil-coil based strategy for assembling proteins to design a cage that assembles and disassembles in response to binding divalent transition metal ions, such as nickel. A metal-dependent coiled coil design that was previously shown to assemble into a homotrimeric parallel coiled coil in the presence of divalent transition metals was used. They genetically fused it to a trimeric protein to facilitate the metal-dependent assembly of this protein into a tetrahedral structure. In the presence of divalent metal ions, this construct assembled into discrete higher molecular weight particles consistent with the formation of a tetrahedral protein cage. Protein assembly was found to be reversed either by the addition of metal chelators or by decreasing pH. To design a metal-dependent protein cage, researchers use a trimeric esterase, or tri-est, as the PBB to assemble tetrahedral, octahedral, and icosahedral protein cages. To assemble a trimeric esterase into a metal ion-dependent tetrahedral cage, a de novo designed 4-heptide coil-coil designed to oligomerize into a parallel trimeric 3-helix bundle in the presence of divalent transition metal ions was used, and a metal binding site was introduced in between to allow for 6 coordinate metal binding sites with his residues at 2 places per coil. The metal binding coil-coil was genetically fused to a tri-est at the C-terminus through a flexible 8-residue linker sequence, and a maltose binding protein was appended to the N-terminus to facilitate protein purification, and that can be shown right here. The fusion construct was named TET8M, and this was further analyzed. To equilibrate TET8M with metal ions, the de novo designed metal binding coil-coil was reported to have low micromolar affinities for several divalent metal ions, such as nickel, copper, cobalt, and zinc. They evaluated the potential TET8M construct to assemble into protein cages in the presence of these ions. Nickel appeared to be most affected at causing oligomerization, as concentrations between 20 and 200 micromolar resulted in the largest fraction of TET8M being converted into high molecular weight species. To characterize nickel-mediated assembly of TET8M, size exclusion chromatography was used, and this showed TET8M to elute as a single symmetrical peak consistent with the expected elution for a trimeric form, shown right there. Nickel binding of TET8M showed 2 peaks to elute, indicating that some of the protein was assembling into higher molecular weight species and some wasn't. The assembled protein eluted at the same elution volume in a symmetrical peak, suggesting that the assembled protein was fairly homogeneous, that the assemblies were kinetically stable and did not re-equilibrate to form a mixture of assembled and unassembled species. In contrast, when the assembled species were re-chromatographed in buffer lacking the divalent metal ions, such as nickel, the protein eluted as a mixture of assembled and unassembled forms. Complete disassembly of the complex could be achieved by SEC and tris HCl buffer containing EDTA or with a buffer of pH 4.5. To characterize the metal-dependent assembly of TET8M, DLS, native page, and TEM were used. Dynamic light scattering, or DLS, was used to measure the hydrodynamic radius of particles. They examined the effect of nickel ions on the particle size of TED8M. Scattering spectra were recorded of 20 micromolar solutions of TED8M at pH 8 in tris HCl buffer in the absence of divalent metal ions and in the presence of 100 micromolar nickel chloride. In the absence of metal ions, the hydrodynamic diameter of TED8M was around 11.9 nanometers, which is consistent with the diameter of the trimeric form of the protein. In the presence of nickel ions, the diameter of TED8M increased to about 23.8 nanometers, which is in arrangement with calculated diameter of around 20 nanometers for a tetrahedral protein cage. DLS spectra of TED8M were recorded after the nickel ions were removed by chelation with EDTA or the pH reduced to 4.5 to dissociate the coiled coils. The average hydrodynamic diameter for the EDTA treated sample was around 12.6, and for the pH sample it was around 7.9, and these results are consistent with the TED8M returning to the trimeric state. The assemblies of TED8M were also studied using the Nano-cage to assess the homogeneity of protein assemblies, and the Ni-TED8M complex was cross-linked using the BS3 reagent prior to electrophoresis to prevent dissociation of the assembled material. The cross-linked TED8M sample migrated as a much larger species than the untreated TED8M sample, indicating nickel-mediated assembly of the protein. Control experiments confirmed that treating TED8M with BS3 in the absence of nickel-2 ions did not cause cross-linking into higher molecular weight species, and that can be seen right here. Particles formed by TED8M were visualized by TEM. The trimeric form of the protein appeared as small, unassembled species at first. In the preliminary experiments, they found that a nickel TED8M complex is partly dissociated on the EM grids and might be due to interaction between the coiled coil domains and the copper ions on the surface of the TIM grid. The problem was overcome by covalently cross-linking the assembled protein with the BS3 reagent, and when cross-linking of the assembled protein with BS3 reagent, the material appeared as discrete homogeneous particles. The average diameter for each particle is measured to be around 18 nanometers, shown right there. And lastly, the catalytic efficiency was also analyzed by turnover number. The trimeric TED8M construct and the high molecular weight species assembled from TED8M in the presence of nickel were compared to the unmodified esterase. The results confirm that neither the assembly process nor the fusion of the coiled coil with NBP domain significantly alters the function properties of trimeric esterase.
Regarding the discussion section, the project team was successful in constructing a metal-dependent protein cage using a symmetry-based design strategy with coiled coil sequences that oligomerized from binding to divalent transition metals. However, the assembly process was not very efficient and was highly dependent on the transition metal concentrations. The team observed that these problems could be resolved by optimizing the coiled coil interaction strength and the metal binding interaction strength. Regarding the materials and methods section, size exclusion chromatography, dynamic light scattering, transition electron microscope, and native page were all used to characterize the TED8M nickel 2+ complex. Size exclusion chromatography was used to purify the protein. DLS was used to determine the hydrodynamic radius, and negative stain TEM was used to determine the diameter of the protein to compare with the hydrodynamic radius.